This meeting is being recorded.
We begin chapter 10, section 10, with this reaction here, the addition of HBr, and we're told that it's radical addition. We were introduced to this in chapter 9, actually in chapter 8, and then again we looked at it in chapter 9 when we added HBr across a pi bond. So we were told that it would have anti-Markovnikov radioselectivity whenever there was a peroxide present. But we were told that we weren't going to look at the mechanism yet, that we would learn about it later. So here's where we learn about the mechanism when peroxides are used. So without peroxides, we have our starting alkene over here. And without a peroxide, we see the top reaction happen. We have a mechanism which produces a Markovnikov addition. So on the double bond here, the more highly substituted position is brominated, and our product is the more highly substituted product that we see here, where the bromine is at that site. Hydrogen adds where more hydrogen were. The opposite happens, and we have anti-Markovnikov addition with peroxides. And this is because a radical mechanism of action, of this addition rather, happens, and it's a different mechanism. So we have different selectivity. We have a different site that is brominated. So let's see what actually happens. When we have the initiation step, we have a peroxide here, that ROOR, and we see that the oxygen bonds are cleaved, right, between the two oxygen atoms in a homolytic cleavage. It is called thermal homolysis, so that means heat is used to break the bond evenly, and this forms these two radicals down here. So this is an endothermic process. We have to put some energy in, whether heat or light and other reactions in the initiation step. Then we've generated this radical seen here. And in this second step shown, we have hydrogen abstraction. So we create this non-radical here, and we create our bromine radical in this step shown here. And this is an exothermic step. So let's see what happens, right? When energy is released, exothermic steps seem to be, or tend to be, favored. In this next slide here, we see why this kind of takes place. We're told again, we're reminded rather, that there's this lower energy transition state that results when we end up with a tertiary radical versus a secondary radical. So at the more highly substituted position in one case would not produce the more stable radical. So like in this case, so that's why this is an anti-Markovnikov addition. We're going to have a different site selectivity. So this radical here is generated, but this site over here is brominated. So that's why it's not going to be a Markovnikov addition. Let's look at what happens during the propagation steps here. So what happens is we have an addition in this first step here, where that pi bond, one of those electrons, goes this way. The bromine radical donates its electron, and we have this bond form here. At the same time, that other electron gets moved over here to this tertiary site, and the tertiary radical is created. And this is an exothermic step here, this addition. So now we have that radical site interacting with HBr, and we're going to have a hydrogen abstraction in this second step. And this will give us the product of an anti-Markovnikov addition. So the bromine has added to that secondary radical, or that secondary site, and then we had our H addition where that tertiary radical site was, and we regenerate more bromine radicals. And again, we have an exothermic step. So during these propagation steps, you can see that they would be favored steps in the forward direction. They are both exothermic. let's see what happens at the end of this type of anti-Markovnikov addition. So we have these bromine radicals, and it's noted up here that most of the radicals in solution at any given time would be the bromine radicals. So this is the most common termination step. But you should note that we might have a methyl or an ethyl, any any other radical could be involved in a termination with any other radical. So again, the termination step involves any two radicals combining to remove the radicals so this propagation steps do not continue. So let's take a look here at the addition reaction thermodynamics. So we have an anti-Markovnikov radical addition, and as noted, this is generally a spontaneous product-favored reaction. Radical addition, on the other hand, of HCl and HI, we're going to see are generally non-spontaneous, and those would be reactant favored and non-spontaneous in the forward direction. So if you recall, this term here, this Gibbs free energy term, is the sum of the enthalpy, or generally the bond dissociation energy sum, those bonds that need to be broken, and then the bonds that are formed, subtracted, that energy gives us our delta H. And then we have our entropy term, which is temperature dependent. So let's look at the thermodynamics of each of these HBr, HCl, or HI addition, and let's compare and see why one is favored and not the others. So our first step, we have our first propagation step, I should specify. We already have our radical generated. So in this propagation step, our halogen radical, whether it be Cl, Br, or I radicals, adds to our pi bond, and then we generate this most stable tertiary radical. So looking at the values for the enthalpy terms versus the entropy terms for this step over here in this table, we can see that the entropy term is positive for all three, so that doesn't differ. But the enthalpy term is negative for both HCl and HBr, but the iodide radical is so much more stable than the carbon radical that would result that this addition is not thermodynamically favored. So that's why we see this positive value here. But let's look a little bit deeper and see why only the bromination is really favored. So what we see here then is the enthalpy term, and what actually results in the second step of propagation is now a change in sign. So the enthalpy term is now negative for HI, but since the other step was positive, we already can discredit that. So we were between, if you recall, fluorination and bromination, or HBr and HCl being added across the double bond. Now this enthalpy term in the second propagation step is positive for HCl. So that is why that is not spontaneous towards products in this forward direction. So this abstraction of H from HCl is not thermodynamically favored. Again, this is due to that radical, but instead of it being so stable, in this case, the chlorine radical is that unstable. So we would be reactant favored in this case. So the next slide here, in section 10, we're going to just do a summary here, but now with our anti-Markovnikov addition happening, if a new chiral center is created, so this would be an achiral molecule to a chiral center, we would create a product that has a racemic mixture of configuration. So substrate is achiral, racemic mixture. If we started with a stereocenter in our substrate, then we would end up with not a racemic mixture, but we would get diastereomers. So a mixture of sites that could end up with this bromination. So we could have multiple chiral centers if we already have a stereocenter with our starting material. So we will continue with section 10.11 in the next video.